we are going to continue discussion about the diffusion process in a semiconductor, and last time we discussed about the diffusion process. The substitutional diffusion is mainly happening for the dopant atoms, but the impurity atoms, most of the impurity atoms are diffused with the interstitial diffusion, which is much faster than the substitutional diffusion. Okay, and the diffusion process can be divided into two processes. One is a pre-deposition, and the other is a driving process. And we try to solve the fixed second law to get the profile. And here we have initial, we have two boundary conditions and one initial conditions. Okay, this is the initial conditions, right? And these two boundary conditions, the first boundary condition is very important, which says the surface concentration is always maintained at the concentration limited by the solid solubility limit. Okay, and so that is a fixed value, and most of the dopants should have high solubility limit in order to have a low resistance. Okay, and we assume the infinite long crystal, so that when X get infinity, there's no dopant atoms. Okay, and this is the initial condition, where initially we started with the pure wafer. Okay, and if you use these boundary conditions and fix the second law, then you're going to have a complementary error function, and the main purpose of the pre-deposition is the charging, loading the dopant atoms on the silicon wafer, so that instead of this profile, this charges total number of dopant is important. So this total number of dopant can be obtained by integration of the dopant concentration from the surface to the infinity, obviously. Okay, and then that ends up with this equation, and that is important. Here again, we are having the solubility limit in this total charges loaded during the pre-deposition thing. This is the solubility limit, and as I mentioned earlier, most of the dopant has a high solubility limit, like a 10 to the 21. It's pretty high, okay? So that we can have almost a metallic resistance when the silicon is doped with this dopant atoms. And the other element, which is not really a dopant, they have a relatively low solubility limit, and we are going to discuss about these elements, why it cannot be used as a dopant shortly. Okay, and this is the pre-deposition dopant profile. That's a complementary error functions, and let's see, in the driving process, we have to have 4 boundary conditions, because the first boundary conditions we are going to cut off the source of the dopant so that the normal flux is going to be implemented into the silicon wafer, so that this fixed first law, which is related to the flux, that has to be zero. There's no source during the driving process. And that has the derivative form, so that we need another one more boundary conditions to solve the fixed second law. And this is the infinite crystal assumptions. It's the same to the predeposition condition thing. And this is the initial conditions for the drive-in, because most of the drive-in process has to be done after the predeposition, and then during the predeposition, this is the dopant profile we can obtain during the predeposition. So the initial conditions for the drive-in process should be represented as the complementary error functions after the predeposition. Okay, and one more boundary conditions which we are going to use is the delta function for the dopant profile, and that means drive-in diffusion length for the drive-in is very much larger than that of the predeposition, so that during the predeposition, no significant, considerable diffusion happens during the predeposition. If we can assume this, then the solution is going to be simple like this. That is a Gaussian profile. But if we cannot assume that, I mean, predeposition, if the predeposition temperature is very high or comparably high to the drive-in, that of drive-in, or the predeposition time is comparable to the drive-in time, then this assumption is not valid. And if this assumption is not valid, then we can solve the fixed second law, and the solution is this complicated equations. This is a pretty much complicated solutions of the fixed second law. And this figure shows that if the criteria for the assumption is the four, the drive-in diffusion length over predeposition drive-in length, that should be greater than 16, okay? Then we can use simplified answers, simplified solutions. If it is less than 16, then as you can see in this computer simulation, okay, is 0.25 is the coupled solution criterion, okay, that is 4 here. So this 0.25, then it is less than 0.25, then the exact solution or the coupled solution has the same answers, as you can see here. But if it's more than 0.25, like 1.0 here is shown in this plot, you can see very much different. So the criterion is empirically, that is 4. This criterion is 4. Okay? But in most of the semiconductor processes in the industry, this criterion can be satisfied so that this simplified solution is good enough to be used. Okay? Okay, so it can be said that during two things are important. One is pre-deposition. The charges that is going to be loaded is going to be Q T now is equal to 0 and x t dt, and that is 2 over pi root dt of n naught. Okay, atoms per square centimeter. Because it's that most of the dopant are concentrated at the surface, so we are going to use the square centimeter instead of centimeter cube. Okay, and the important answer that we obtain is after the pre-deposition, after drive-in, that is after pre-deposition, okay? After drive-in, the dopant profile can be represented with the Gaussian T minus x squared over 4 dt. Atoms per cube. Okay, that is the actual profile, and that will determine the junctions. After the diffusion process. So let's see. In the pre-deposition, pre-dep, if you just plot the profile, then during the pre-deposition, the source of the dopant is continuously supplied so that as time goes by, the profile is going to look like this, and here that is the solubility limit, right? Solubility limit. But during the drive-in, first we have a profile like this, but the source is no more supplied. So that as time goes by, the profile now is going to look like this. Okay, that is the difference, and this is the complementary error functions, and this is the Gaussian profile. And most of the profile has been tabulated so that you don't really have to solve the equations whatsoever. Okay. Now let me just introduce the diffusion systems. I think the requirements for the dopants, as I told you before, we should have a maximum solubility limit in order to have a low resistance, right? And no damage to silicon substrate. The silicon substrate is a single crystal. So if you mix with dopant atoms to the single crystal silicon, if it destroys the crystallinity of the silicon, then it cannot work as a dopant atoms. Okay, so no damage should occur during the doping. And the formation of etchable glasses on the silicon surface. This will be discussed a little bit later, shortly. And the reproducible, of course, and then the batch processor should be passable, right? And the system, if we use the gas for the dopants, then we do have dopant gas and reaction gas and the inert gas. So this inert gas we usually call the carrier gas. That this inert gas carries the dopant gas, dopant atoms into the system. Without this inert gas, carrier gas, the concentration of the dopant atoms in the chamber or furnace is too high. Okay? And if you use a liquid source, then this liquid source, we use this apparatus to have the bubbles and whatever, to have a liquid source. And if we use the solid source, solid source is not shown here, but for this is for the case for the borons. Okay. Let's discuss about the system a little bit later. Here, p-type dopants in silicon, the substitutional atoms should work as a dopant, right? So for the silicon covalent bonding system, if you want to dope with the n-type, then this 4-valence electron material has to be replaced with the 3-valence elements like indium, gallium, arsenic, and boron. And if you want to dope the silicon as an n-type, then this silicon has to be replaced, substitutionally replaced with the 5-valence electron elements, which is going to be shown in the next slide. And this p-type dopants, we have this many candidates, but only the boron can be used for the doping elements, because for indium is at room temperature it's not going to be ionized fully because it's deep lying impurities, and the solubility limits is relatively low. And the gallium, the silicon oxide cannot be used as a mask. Okay, so gallium cannot be used as a dopant, and aluminum, it ruins the silicon lattice when it is mixed with silicon. And only boron has a high solubility limit and relatively high diffusion coefficient, so that during the drive-in we have considerable junction depth we can have. And so in a p-type, only boron is available these days in the industries. And in the boron, we have gas phase and liquid phase, bromide and hexa hydrate, the boron. And during the process, as shown here in this chamber, we have two temperature zones. Here is 300 degrees centigrade, and here is 900 to 1100 degrees centigrade for the diffusion process. And what's happening is in the step 1 at the 300 temperature zone, the gas phase will react with the oxygen, okay? So that it's a boroxide. It will form the boroxide. And this boroxide is going to be moved to the high temperature zone for the step 2. And in this high temperature, 900 to 1100 degrees centigrade, this boroxide is going to be reduced with the silicon to produce the element of boron here and the silicon oxide. So this silicon oxide is going to be formed on top of the silicon during the doping process, diffusion process. So when we talk about as a requirement for the dopant, it has a formation of etchable glasses on the silicon surface. It means every dopant will form the silicon oxide on the top during the drive-in process, and that the silicon oxide has to be etched. Okay? If we cannot etch that, then during the drive-in process, the dopant atom is continuously provided, continuously supplied to the silicon, so that we cannot control the exact amount of dopant atoms to be doped in the silicon. So this silicon oxide, after the pre-deposition, has to be removed. And sometimes this glass is formed after the pre-deposition. This glass, it contains a lot of boron, so we call that boroxide borosilicate glass. Okay, we just call it borosilicate glass. This glass sometimes cannot be etched easily, and we have a problem, industrial problem. We do have an industrial problem, and especially the boron case. Borosilicate glass can be etched off after the pre-deposition in a dilute HF. This is the trick in the industry. Usually this oxide, the silicon oxide, should be etched with the HF solutions, okay? But that the silicon oxide is heavily doped. It have a large amount of boron is contained in the silicon oxide, then the silicon oxide cannot be etched with the HF, normal HF. And the industry found that it can be etched with a dilute HF, which is certainly different directions that from the normal practice, right? So if you make a dilute HF, then this heavily boron-doped silicon oxide, borosilicate glass, can be etched. And that has been found in the industry, and that's a kind of trick, okay? And we named it the boron-rich glass, that is boron skin, okay? That we call boron skin effect. Well, the n-type dopant, on the other hand, we have 3 elements are available for the n-type. And for p-type, only 1 element, boron, is available. But for the p-type, we can have phosphorus, arsenic, and antimony there, okay? And this phosphorus has a higher diffusion coefficient than the arsenic and the antimony, so that the arsenic and antimony is good to make a shallow junctions, okay, because the diffusion coefficient is very low. So if you want to make shallow junctions for the N-MOS, for example, you have to use the arsenic or antimony instead of a phosphorus. That choice we have for the N-type, and that is fortunate. Okay, for the phosphorus system, we have a gas phase and liquid phase. Liquid phase, POCl3, we usually call this a POCO in the industry slang or something, okay? And we have step 1 and step 2, low temperature and high temperature zone in the furnace, just like the boron case. And here we have a phosphosilicate glass. Okay, the silicon oxide is formed during the pre-deposition process, and the silicon oxide has to be etched before dry-in. Otherwise, the phosphorus or boron contained in the silicon oxide continues to supply the dopant atoms. It works as a source for the dopant atoms during the dry-in process. Okay? And we have a gas and a liquid source for the phosphorus, but for the arsenic and antimony case, we usually have a solid source because it has a low vapor pressure. Okay? And the system is going to look like this. It's a low temperature and a high temperature zone, as shown here. And at low temperature, it has arsenic or antimony oxide. And then that vapor is going to be reduced in the high temperature zone. Okay? So it has this much. It's just a solid source are available for these two dopant atoms, and this is the open structure of the furnace, and this is the closed system, so that you can maintain the certain level of the vapor pressure of the arsenic and antimony to control the amount of doping. These two systems, the open system and closed systems, both are available. And in the industry, this open system is usually used because it is easy to load and unload the wafer after the doping process. Okay? Now, the next topic that we have to discuss is how we evaluate the doping process. In other words, how can you evaluate how much dopant has been implemented to the wafer? And that, of course, visually we cannot see any difference. The silicon without the dopant and the silicon with the dopant. Visually, it is not distinguishable. But if we measure the resistance, it will show, it will reveal the dopant amount, how much dopant has been loaded on the silicon. Okay, so for example, if we have an NPN bipolar transistor, as you can see here, and the vertical cross section. If you do the Sims profile, for example, so that you just identify each element, M plus and P and M minus. This M minus is the doping level that has been done during the Czechoslovakia, right? In the bipolar transistor, that is the epitaxial layer, as a matter of fact, so that this doping is not done during the Czechoslovakia, but in the MOS transistor, this substrate doping has to be done during the Czechoslovakia. In a bipolar, this total layer is grown by the epitaxial growth, so that during the epitaxial growth, we have a dopant concentration N minus here. So this N minus is the substrate doping, and then we have a P as a base, that as a profile here, and then we have an emitter N plus with a high concentration of phosphorus, and that profile should look like this. And this phosphorus, we do not do the serious drive-in, so that this phosphorus should have a complementary arrow functions. But for the boron, we have a low concentration of the P for the base, so that we do have a Gaussian profile after the drive-in process. And that should be seen after the Sims profile, depth profile, along the depth of the bipolar transistor. But if you measure the resistance along the depth, okay, then the resistance, that is the y-axis. Actually, it is the resistance, but it is converted to the corresponding concentrations. We have a equation or table which is one-to-one relations between the resistance and the concentrations. We are going to discuss about it shortly. So this is actually, you can think, is a resistance. And along the depth, we have M plus resistance corresponding to the M plus, and then we have a very high resistance at the junctions. When it's M plus and the P, if the amount is equal, then it's all dopant atoms are compensated, we should say, and then the resistance is very high, and then that is converted to the concentration, then we have a zero concentration of the dopant. Things like that, okay? And then we have a P profile, and then M minus profile like this. So if you do the Sims profile, we're going to have this results, and if you measure the resistance to get the profile, then we have a little bit different profile, which is looking like this, okay? But basically, the junctions, determination of junctions, we can use both Sims profile or resistance measurements. Okay, and for the diffusion profiles, every thermal cycle has to be added together to determine the final diffusion length. So all the heat treatment should be added